Hi, everybody. It's Professor Mitchell, finishing up our work with Chapter 11 today. We are talking about contingency tables. So we now consider methods for analyzing contingency tables, which include frequency counts for categorical data arranged in a 2-by-2 table. We present a method for conducting a hypothesis test of the null hypothesis that the row and column variables are independent of each other. And we will consider one variation of the basic method. I will talk about the test for homogeneity. However, I will skip these other two tests. So a contingency table, or two-way frequency table, is a table consisting of frequency counts of categorical data corresponding to two different variables. One variable is used to categorize rows, and a second variable is used to categorize columns. In a test of independence, we test the null hypothesis that in the contingency table, the row and column variables are independent. That is, there is no dependency between the row variable and the column variable. And just like with anything else, this will make a lot more sense when you see an example. So the objective is to conduct a hypothesis test of independence between the row variable and the column variable in a contingency table. The notation we'll be using, about half of it should look familiar from the last section. O will represent the observed frequency in a cell of a contingency table, and E will represent the expected frequency in a cell, found by assuming that the row and column variables are independent. Next, we will use R to represent the number of rows in the contingency table, not including labels or row totals. And C will represent the number of columns in a contingency table, again, not including labels or column totals. The requirements are that the sample data are randomly selected. The sample data are represented as frequency counts in a two-way table. And finally, for every cell in the contingency table, the expected frequency E is at least 5. And just like in the last section, there is no requirement that every observed frequency must be at least 5. The null and alternative hypotheses for this type of test will be: the null hypothesis will be that the row and column variables are independent. The alternative will be that the row and column variables are dependent. The test statistic for a test of independence is the same as the one that we were using in the last section. It is chi-square, and it's found by calculating O minus E squared divided by E for each cell, and then adding all of those together. So again, O is the observed frequency in a cell, and E is the expected frequency in a cell. And unlike in the last section, the way that you calculate E for each cell is to take the row total times the column total and divide by the grand total. And when we get to an example, I'll try to say a few words about why that calculation makes sense. P-values are typically provided by technology. In fact, for a chi-square test, that's the only way that we know to get exact p-values, or a range of p-values can be found from table A4. Alternatively, you can use critical values. The critical values can always be found in table A4. The degrees of freedom will be R minus 1 times C minus 1. And again, R is the number of rows and C is the number of columns. And just like in the last section, tests of independence with a contingency table are always right-tailed. That's kind of nice. One less thing to keep track of. The relationships among key components in a test of independence: compare the observed O values to the corresponding expected E values. And if the O's and the E's are generally pretty close together, then that means that sum of O minus E squared divided by E will be relatively small, which means it'll lie in this white region here somewhere. And in that case, we would fail to reject the null hypothesis of independence, okay? On the other hand, if some or many of your O's and E's are far apart, that would mean that the sum of the O minus E squared divided by E will be large. And that would put you in this green region, which is our rejection region. And that would also give you a small p-value. So in that case, you would reject the null hypothesis of independence. Remember, if p is low, the null must go. All right, we'll just stick with the same saying there. The null hypothesis is independence. All right, so here's our first example. The table on the next slide is a contingency table with 4 rows and 2 columns. The cells of the table contain frequency counts. The frequency counts are the observed values, and the expected values will be shown in parentheses. I'm also going to show you how to calculate these expected values. The row variable identifies the treatment used for a stress fracture in a foot bone, and the column variable identifies the outcome as success or failure. In other words, the treatment was a success or it was a failure. Refer to the table and find the expected frequency for the cell in the first row and first column where the observed frequency is 54. Now you'll see right away that they've gone ahead and given me the answer. All right, but I do want to show you how they got that number. So we'll do that in a second. We'll just kind of look this over. I'm going to use Excel to show you how you can come up with all of these numbers, because in the next example, we're going to conduct the hypothesis test, testing the claim that the chances of success or failure are independent of the type of treatment used. So in that case, we will need all of these numbers, okay? But for this example, they're just asking about the 47.478, okay? So again, the way that you calculate all of those expected frequencies is by taking the row total times the column total divided by the grand total. All right, now I think this might be a little bit more clear when I show you my Excel spreadsheet. The first cell lies in the first row with a total frequency. No, that's not right. Hold on one second here. Never mind, I misunderstood. That's correct. The first cell lies in the first row with a total frequency of 66. See, 54 plus 12 is 66, so that's the row total. And the first column with a total frequency of 182. So these 4 numbers here, 54, 41, 70, 17, add up to 182. The grand total is the sum of all the observed frequencies in the table, which is 253. You can take my word for that for now. You'll see it in the Excel spreadsheet. Therefore, the expected frequency of the first cell is 66 times 182 divided by 253, which comes out to 47.478. We can interpret the expected value by stating that if we assume that success is independent of the treatment, then we expect to find that 47.478 of the subjects would be treated with surgery and that treatment would be successful. So notice there is a discrepancy between the observed value of 54 and the expected value of 47.478. So really the key question is, are there enough of those discrepancies and are they large enough to reject the idea that the chances of successful treatment are independent of the type of treatment used? Okay. All right. So I think I just said this using different words, so we can move on. All right, using the same sample data from the previous example with a 0.05 significance level, test the claim that success of the treatment is independent of the type of treatment. what does the result indicate about the increasing trend to use surgery? Okay, so at this point, I am going to back out of PowerPoint and I'm going to bring up my Excel. So you see that I've set up a table, you know, basically just like the one that we were just looking at. Notice that I have inserted some extra space in between my rows, and that's where I'm going to put these expected frequencies. So the first thing I'm going to do is I'm going to put in my column totals and my row totals. So I'll put my column total right here. I'm going to do this a little differently than you've seen me do it before, because eventually there will be other numbers in these cells. So if I do the usual thing of equals sum and then I just select all of these cells, as soon as numbers pop up in these empty cells, it's going to mess up my sum here. So I want to be very careful to tell Excel that I only want the sum of those 4 cells. So I'm doing that using commas. Okay. And you know me, I always like to use cell references because that makes it much easier to copy and paste things. So for example, I can copy and paste this over here. All right, and then I also need row totals. So for that, I can just do equals this plus this. Okay, I could have used the sum function if I wanted to, but that seems a little simpler. So copy that into all these cells. Let me make this just a little bit wider. Okay. And then for the grand total, well, I think I can just copy this formula over here because then it's going to add up these 4 cells. Okay, so there's the 66, the 182, and the 253 that you saw before. Okay. The next thing I'm going to do is I'm going to put in my expected frequencies. Now I'm going to get a little wonky with you about Excel and formulas. All right, this may be more than you need to know. And if you find it confusing, you don't have to use it. See, I'm very lazy, and so I like to make my formulas so that they will still work when I copy and paste them. Okay, so this is going to be my expected frequency. I can start off by saying that's equal to the row total times the column total divided by the grand total. And I do get that 47.478 that we saw in the last example. The problem I have with this formula is that it's not going to work when I copy it down here. Let me just show you real quick. And that's because it's looking at the wrong things. Oh, see, division by 0 error. That didn't work at all. Okay, so I discovered this on my own one day, I don't know, a few years ago. I figured there must be a way to fix this, so I Googled it and I figured out. All right, so the problem is that if I copy this formula just the way it is into this cell, it's going to take the 92 times, it's going to be looking for a number down here now. And then it's going to divide by number that's supposed to be there, okay? So the way that you can fix that is to put a $sign in front of, I think I need to put it in front of the row numbers. So what that's going to do is when I copy it down, it will always look in row 10. All right, I'm telling it to always look in row 10. Okay, so now I think it'll work when I copy it into these cells here. Okay. However, it's not going to work when I copy it over here. See, division by 0 again. And that's because when I did this formula here, it was looking in E2 for the row total. There's actually 2 problems now. when I look here, it's going to look for the row total over here, and it's going to look for the grand total there. So I can actually make this formula even better by putting a $ in front of the E for the row total. The row total is always in column E, and the grand total is also always in column E. And now this formula is going to work in every single cell that I need it to work in. And let's see, well, there's really no need to paste it over those. Those work just fine, but I am going to paste that formula here, 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 and here. So those are our expected frequencies. All right. So what I need to do now is for in each category, and at this point I don't need the 2 cells anymore. It was just easier to leave it the way it is. I need to, in each one of these 8 cells, right, wherever a row and a column meet, I need to calculate O minus E squared divided by E. All right, so to do that, I'm going to say equals, parenthesis, there's my O, there's my E, I need to square that, and then I need to divide by E. And I don't need any $ in this formula because everything matches up perfectly. So in other words, it's always going to look here and here for the O and the E. And as long as I always put this, in the same sort of relative position, then it's always going to be looking in the right place. Okay. All right, so the test statistic for this hypothesis test is the sum of all of those numbers. So to finish this off, I'm going to say equals sum, and now I can just grab all of these numbers, and their sum is about 58.393. I just love Excel. All right, so let's go back to the PowerPoint. Okay, so first checking the requirements. On the basis of the study description, we will treat the subjects as being randomly selected and randomly assigned to the different treatment groups. The results are expressed as frequency counts, and the expected frequencies are all at least 5. The lowest expected frequency is 6.174. So that satisfies the requirements. The null and alternative hypotheses are as follows. The null hypothesis is that success is independent of the treatment. The alternative is that success and the treatment are dependent. The significance level is alpha equals 0.05. Because the data are in the form of a contingency table, we use the chi-square distribution with this test statistic. And you just saw me doing this over in Excel. 58.393. All right, so to get the p-value, we'll use technology. If using technology, results typically include the chi-square test statistic and the p-value. So using Excel stat, which we haven't used, Excel stat was able to come up with the 58.393, and it says that the p-value is less than 0.0001. So what I want to do now is back that up with what we usually use, which is chi-square distribution calculator. Remember, for chi-square, we don't use StatTrek because it only, I remember that one time, it only gave me 2 decimal places. That was not good enough for my math lab. So we use SocSciStatistics.com. So let's pull that up. And okay, so it's asking for the chi-square score, which was 58.393. It's asking for the degrees of freedom, which we haven't talked about for this example. The degrees of freedom is going to be the number of rows minus 1. There are 4 rows, so 4 minus 1 is 3, times the number of columns minus 1. There were 2 columns. 2 minus 1 is 1, so 3 times 1 is 3. The significance level is 0.05, and I hit calculate, And it's telling me that the p-value is less than 0.00001. And so this result is significant at a 0.05 significance level. All right. Okay, if you're using table A4, first find the number of degrees of freedom, which we have to do to use our website anyway. So again, 3 degrees of freedom. And let's look at table A4 here real quick. So here's table A4. If I go to the 3 degrees of freedom row, the largest chi-square value in this row is 12.838. So they have a nice picture in the PowerPoint, but 58.393, I think it was, is much, much bigger than 12.838. So that means the p-value will be less than 0.005. Right? We got a much better, more specific answer from technology, but that would be good enough for what we're doing. Okay, because the p-value is less than the significance level of 0.05, we reject the null hypothesis of independence between success and treatment. And I just want to point out to you real quick, when you look over these O minus E squared divided by E values, they give you some insight into what really drove up that total chi-square score. For example, I'm noticing here this 24.56 really accounts for, almost half of the value of the total. So there was really a huge discrepancy between the observed 51 failures among people who were wearing weight-bearing casts versus the 25.8 that I would have expected if the type of treatment had no effect on the chances for success. So I just wanted to point that out to you. Let's see. Okay, so using the critical value approach, if the critical value method of hypothesis testing is used, the critical value is chi-square equals 7.815. Let's look at that real quick. So we want the area to the right of the critical value to be 0.05. Going down to the 3 degrees of freedom row, you see this 7.815. Okay. All right. So here's the nice picture. My rejection region is in green. If my calculated chi-square value had come out to be anything in this region, I would reject my null hypothesis, and it really came out to be much, much, much bigger than the critical value of 7.815. So that would be another way to tell that you reject the null hypothesis. It appears that success is dependent on the treatment. Although the results of this test do not tell us which treatment is best, we can see that the success rates of 81.8%, 44.6%, 95.9%, and 77.3% suggest that the best treatment is to use a non-weight-bearing cast for 6 weeks. These results suggest that the increasing use of surgery is a treatment strategy that is not supported by the evidence. Okay, so now a test of homogeneity. A chi-square test of homogeneity is a test of the claim that different populations have the same proportions of some characteristics. In a typical test of independence, this is how this differs from what we were just doing. In a typical test of independence, sample subjects are randomly selected from one population and values of 2 different variables are observed. In a typical chi-square test of homogeneity, subjects are randomly selected from the different populations separately. In conducting a test of homogeneity, we can use the same notation, requirements, test statistic, critical value, and procedures given previously, with the exception that instead of testing the null hypothesis of independence between row and column variables, we test the null hypothesis that the different populations have the same proportion of some characteristic. All right, so for the example, we'll use the lost wallet experiment. The next slide lists results from a Reader's Digest experiment in which 12 wallets were intentionally lost in each of 16 different cities, including New York City, London, Amsterdam, and a bunch of others. Using a 0.05 significance level with the data, we will test the null hypothesis that the cities have the same proportion of returned wallets. The Reader's Digest headline, Most Honest Cities, the Reader's Digest Lost Wallet Test, implies that whether a wallet is returned is dependent on the city in which it was lost. Test the claim that the proportion of returned wallets is not the same in the 16 different cities. So here is the data. So you can see, for example, that city number D, letter D, appears to be a very honest city. 11 out of the 12 wallets were returned, as opposed to city J, where only one of the wallets was returned. Okay? And everybody else falls somewhere in between. So, I mean, it looks like it depends on where the wallet was lost, but you know how we do it. We want to know if these results are statistically significant. So first we'll check our requirements. Based on the description of the study, we'll treat the subjects as being randomly selected and randomly assigned to the different cities. The results are expressed as frequency counts, and the expected frequencies are all at least 5. We will verify that in Excel. The null hypothesis and alternative hypothesis will be: the null hypothesis is whether a lost wallet is returned is independent of the city in which it was lost. And the alternative will be a lost wallet being returned depends on the city in which it was lost. Okay, so here's a StatCrunch display. The accompanying StatCrunch display shows the test statistic of chi-square equals 35.388 and the p-value of 0.002. Because the p-value of 0.002 is less than the significance level of 0.05, we reject the null hypothesis of independence between the two variables. In other words, it appears it does depend, the chances of getting your lost wallet back does depend on the city in which you lost it. So I thought it might be nice one more time to go over to Excel. And I have this all set up. So here are my observed frequencies. And I've already put the row totals and the column totals. Okay. All right, so remember, your expected frequency is the row total times the column total divided by the grand total. And then in order for my formula to copy and paste properly, I'm going to pin the row reference there, and I'm going to pin, I'm sorry, that's a column reference, and I'm going to pin this in column 6. Okay. Row 6, I said it right the first time. Okay, so yeah, S is a column and 6 is a row. Okay. All right, so let's see, I think this will copy and paste correctly. Copy it, whoops, don't want to copy it up there. Okay, so notice they're all 5.625, and I think I can help you understand this a little better. If you add up all of the wallets for all 16 cities, 90 of them were returned and 102 were not returned. So if it's true that it doesn't make any difference which city you lose your wallet, it has the same chance of being returned, then I would expect roughly 90 out of 192 wallets, that proportion, to be returned in every city. Well, 90 over 192 times 12, which is the total number of wallets, is how you get that 5.625. Okay? And then if I copy that, actually I can copy it all the way across here. Oops, I did something wrong. What did I do? Okay, messed up my formula somehow. 4C6 S8. I see what I did. It's because in the grand total, I have to pin both the row and the column. And I forgot to do that. So now if I copy this, and again, I really am getting wonky with the Excel. If you find the cell references confusing, you don't have to use it. It just means you'll have to do a little bit more work than I'm doing. All right, so these are the expected frequencies for the wallet not returned numbers. I would expect them all to be, close to 6.375. So now I'm going to calculate my O minus E squared divided by E for each cell. So here I'm going to say equals, parenthesis, O minus E squared divided by E. All right. So now if I copy this all the way across here, it's interesting. I don't know why it made column C bigger to, accommodate all these extra decimal places, and it didn't do that in the other columns. I noticed that before, and anyway, doesn't matter. All right. And then notice I already had my grand total sum formula program down here. So there's the 35.388. So now why don't we hop over to SociSciStatistics.com and see if we can get the p-value that they were telling us about. So 35.388. And then the degrees of freedom, we have 2 rows. So 2 minus 1 is 1, and we have 16 columns. Remember, there were 16 cities. 16 minus 1 is 15. 1 times 15 is 15. Significance level is still 0.05. So if I press calculate, there is the p-value 0.002165. Okay. In the PowerPoint, they said 0.002. All right. So, because the p-value of 0.002 is less than the significance level 0.05, we reject the null hypothesis of independence between the two variables. Whether you're going to get your wallet back really depends on what city you're in. We reject the null hypothesis of independence, so it appears that the proportion of returned wallets depends on the city in which they were lost. There is sufficient evidence to conclude that the proportion of returned wallets is not the same in the 16 different cities. Remember, that was the original claim, so there is sufficient evidence to support this claim. And that's going to do it for section 11.2. Thanks for watching. We'll see you next time.